Hello everyone, my name is Samuel Wilson and today I will be presenting our work on hyperdimensional feature fusion for out-of-distribution detection. This is a joint work between the QUT Centre for Robotics and the University of Adelaide's Australian Institute for Machine Learning, with my fellow co-authors Toby Fisher, Nico Sunderhoff and Faraz Dayeb. It is well known that neural networks perform well when they are tested on data that closely matches their training distribution. However, when these networks are presented with out-of-distribution samples, they are often overconfident in their erroneous predictions. More concretely, neural networks fail silently on out-of-distribution samples. Furthermore, in many applications, this backbone network is often infeasible to retrain due to the computational complexities associated with either the architecture or datasets involved. Since we cannot trust the outputs of the network, we must look inside into the features of the network, where we encounter the problems of high dimensionality or the curse of dimensionality, and the best features are not known a priori. In order to address these challenges, we leverage hyperdimensional computing as a framework for dealing with high-dimensional data. In hyperdimensional computing, associations between data points are stored as vectors in associative memory, which we construct through a set of standardized operations. For our purposes, we care about bundling, which creates a new representation that is similar to all of its inputs, binding, which creates a new representation that is dissimilar to all of its inputs, and encoding, which projects data from some original space into the hyperdimensional space. We utilize these operations in our work as our specific implementations of these hyperdimensional computing operations. In order to leverage the multi-scale feature maps from a neural network for out-of-distribution detection, we first have to extract the feature maps from the backbone of the neural network. Once we have these feature maps, we then spatially pull them down to vector representations in order to integrate with our hyperdimensional computing framework. Now that we have our extracted feature vectors, we wish to combine them in a hyperdimensional space. We accomplish this by encoding them through an orthogonal projection up to the hyperdimensional space. Once all of our vectors are in this hyperdimensional space, we then simply bundle across all of the layers to create a single image descriptor vector. Finally, we repeat this process for all of the in-distribution training samples belonging to an individual class, and bundle across all of these image descriptors to create a singular representative class bundle vector. During testing, we measure the angle of any test time image descriptors to the nearest class bundle. As the figure below shows, we find that in-distribution samples in the blue line are often much closer to the class bundles than out-of-distribution samples in the other colors. Our results show that HDFF is competitive with state-of-the-art OOD detectors whilst being significantly faster during inference. Additionally, HDFF is compatible with different training methodologies and post-hoc detectors. Additionally, we find that visually similar samples will cluster close to both class bundles and to each other in the hyperdimensional space. In practice, this means that we can determine how visually similar a sample is to a class bundle based on its angle to that class bundle, and we can also determine the visual similarity of individual images by comparing their image descriptors. Thank you for listening. If you're interested in learning more, please come find me at the poster session, or you can find our code available at GitHub at the link below. Thank you.